So welcome back to the Calculus Analytic Geometry. So from today on, we will carry on our discussions on Calculus Analytic Geometry. So the way we will do it is that we will, I'll record the lecture, unfortunately in an empty class, and upload them on YouTube, and then we will have later a Zoom session to meet with your questions and queries that you have actually. Okay, so what we are going to do, what we are going to do today is really what you call the applications of derivative. I mean, what we did previously, so what we have covered in detail in our physical classes is really the differentiation rules. I hope that you are very well aware that if you have been given any kind of implicit or explicit function, then you know how to differentiate it, with respect to the independent quantity. Okay, so what we would like to do next is that, we learned a lot of differentiation, but what are the uses, what are the applications of this differentiation actually? So this is what that I'm going to focus on. That in upcoming set of discussion, our task is entirely going to be to show you, to convince you that differentiation, the differential calculus, is a very useful tool, and you can apply it almost anywhere where the two quantities are changing. So the one is independent, another is independent. You can answer a hell lot of questions out of these differentiation technique about the things in the computer science, about the things in the natural sciences and biological sciences, and the things in the social sciences actually. So it's a very natural tool. So the target today, the first target today is really to show you that how a single idea of derivative can model or capture a lot of natural phenomena. So this is what is going to be our first task, is to show you that how in different kind of natural settings, natural environment, physics and say biology, mechanical engineering, in different kind of varieties of situations, a single phenomena is basically simply derivative. A single derivative, a single notion of derivative can model many things actually. So this is what is one of the first tasks of our, and then obviously we're going to do a lot of applications of it actually. And obviously I'm going to leave some of the things for you to do at your home site. Okay. So let's imagine I have a function. You can say that, this is kind of represent, say, time axis, and this is representing, for example, something that depends on time. Maybe we can call it, let's call f of t to be revenue of, say, a software house actually. A software company that creates the software actually. So imagine, it turns out that when you plotted the revenues of a software company, you get, some kind of a smooth curve actually. So this is a smooth curve that kind of represents the revenue or the earnings of the, software company. And say this time is representing, say, the time in, months. So months or maybe days actually. So let's talk about, say, let's imagine that this time is representing the months actually. So 0 being the time when the company was initiated, okay, and then what happens that over the time the earnings goes up, then earnings a bit slows down and then goes up and so on and so forth actually. Okay, so you can have multiple interpretations. We have to have long discussions over that, how to interpret what do you call functions actually, and how it says it, how a curve of a function tells you a story actually. Okay, so that how a curve can represent what you call a big amount of data, okay, or how you can fetch a lot of information out of the curves actually. So that's not my topic of discussion today, but we had very long discussions over this actually. So imagine if I take an interval, okay, so let's take say A and B. So A is representing some number of months and B is representing some number of months, and then at A months, what were the earnings say of the software house? The earnings of the software house were this much high, that is that the earnings were f of A actually. So the f of A is representing what do you call say earnings in the thousands of the dollars actually. Okay, so in eighth month, the earnings of the company was f of $8,000, and on bth month, say, the earning of the company was this, which is a little bit of what do you call f of b $1,000 actually. Okay, let's call this. Now, in this period, if you are interested in computing that what is the average change in my earnings actually, okay, what are the average change in my earnings that has happened in this interval, then what you need to do, you need to compare the change in the revenue in the earnings with the change in the time. So the average, let's say average rate of change, okay, in say f, okay, is what? Okay, where f is representing your earnings over the time, is what do you call f of b minus f of a over b minus a. So this is what it's going to be. Now, what would be the interpretation of it? How to read it? For example, if I give a and b some numbers. So the a is say 3 months and b is say 5 months, and f of a is say $10,000, okay, so $10K, and f of b say represents what do you call I don't know, maybe $18K, okay, something like that. Then what would be the average rate of change in between 3 to 5 months? So it is going to be 18 minus 10 over what do you call 5 minus 3, so it's going to be $4K. So it's going to be 4 actually. But this 4 has a meaning actually. And this is what that we need to know and that we need to keep in head, is that this 4 has a meaning. So what does the 4 represent? 4 represent that between 3rd and 3 to 5 months, the company has earned around $4,000 per month. Per month. If this is month axis and this is thousands of dollars, then this is what that you have in your if the average what do you call a rate of change in your earnings, in the earnings of the software house, what do you call during this time period. So this quantity gives you that how much on average f is changing in this interval. So this is what that you need to keep in mind, and that's an important thing. So let's move on a little bit more. Now, I mean, if you remember, we also talked about a little bit about that. Okay, if say this is A, okay, so maybe I can talk about the same curve. Okay, same curve. Let's talk about the same curve. So what does the average is representing? Average is kind of representing, you can say that, okay, you have a secant line actually that passes through these both points. I must use some other color chalk. That's a secant line that passes through, what do you call this points? Now we also talked about the, what do you call the definition of the derivative, and we said that, okay, if we bring these points closer, can you think that what will happen with, what do you call this secant line? In other words, if these points are coming closer, their outputs will also come closer actually, and the line will gradually become, okay, like this and like this, and eventually when they are going to be really near to each other, the line will almost become like a tangent line actually. Okay, the line will almost become like a tangent line. Okay, so I'm not going to get into the details of it because we have discussed it already. Okay, so in other words, if you have, for example, so if I represent say f of b minus f of a is the change in f, and b minus a is the change in time, then change in f, the ratio of change in f with the ratio of time is basically giving you the average rate of change. So this is average rate of change. Okay, and what do you mean by rate? Rate, why are you calling it rate? Because it gives you really a rate actually, that okay, it's the 4k-1000 per month actually. So on average, the earnings are increasing by 4k-1000 per month. So that's like a rate. So you have this average. Now, what will happen if I bring these 2 points together actually? If I bring these A and B together. So when I'm saying that, okay, let's bring A and B close to each other. So this is equivalent to say that let's, what do you call, decrease this change in interval. Let's decrease this change in interval delta t, and let's take that to 0 actually. So what will happen to this average rate of change when this delta, the change in time, is going to 0? Obviously, if the change in time is going to 0, in other words, these 2 instants are coming together, okay, then, okay, so if I say that I have like this, okay, and I have these 2 points, say A and B, okay, and these 2 points are getting closer. So if these 2 are getting closer, their outputs will get closer. If the inputs are getting closer, the outputs will get closer too. And when the inputs are really close to each other, this secant line will become a tangent line. And then, in other words, you can approximate locally this curve by a tangent line. The curve is going to behave in the same manner the way the tangent line is behaving actually. So if you want to know that, okay, how much my curve is increasing, is going up, what we can do is you just look at that point, the slope of the tangent line. Okay? So we had all these discussions very long actually, in detail in our classes. I'm not gonna bore you with again all this stuff. Okay. So if you're talking about a really tiny time that is close to 0, then the change in f would be really tiny. And then this quantity is also going to be tinier actually. And let's give that quantity a name, what do you call that, df by dt. And now this guy is really instantaneous change actually. Instantaneous change. Okay. Instantaneous rate of change. Okay. So for example, in some situations, average rate of change gives you a good, what you call information, but in some situation, you are very much interested in that how much the change is taking place instantaneously. For example, let's talk about the stock actually. Okay, so you have bought some stock, okay, and and we know that the price of the stock of a company, could be a good company, be a bad company, whatever. Okay, the price of a stock always evolves actually. It goes up and down. Okay, it goes up and down. So if you are trading, for example, some stocks in a given day, okay, then in that given day, you know that the price of a stock will go up and down. Okay. Now, if you are a good investor, what you would like to do, or if you want to make money, what you would like to do, you want to buy cheap and sell, what do you call, expensive. If you're gonna buy a thing cheap, so I bought this chalk for example, this box of chalk for $2, and I get an opportunity to sell it at $3, then that means that I made a $1. Okay. Now, in a day, if the stock is continuously going up and down, then as an investor, you need to keep a track of the fact that, okay, this stock is going how much down actually. Maybe it has hit its lowest value, so buy it. And on the same, what do you call, day, if the stock goes up, and it goes up actually depending on demand and supply, okay, and reaches to a point where you think that, okay, it's no more gonna go up, so you sell everything, or you sell it, and you get that difference as profit actually. Okay, could be loss as well. Okay, are you getting the point? But in doing all this, in dealing with what do you call a stock market, the instantaneous rate of change in the stock price plays an important role. Okay, that plays an important role. The average value is also important, but the instantaneous rate of change in the stock price plays an important role because the investors are going to make decisions based on it. Okay. So in some situation, average rate of change gives you a good piece of information, but in some situation, instantaneous rate of change gives you a good piece of information actually. And my objective today is to show that how this funny looking differential, the derivative df by dt, a single idea can model a lot of things in the natural world actually. Okay? In the natural world. Alright. So let's just start with one of, say, example of it as in physics actually, maybe in mechanics. Okay. So let's just start with a little bit of physics. So imagine I have a particle that is moving in such a way. Okay, and we talked about various kind of examples of such when we were discussing the theory of functions and limits actually. Okay, so we talked about the velocities, the displacements and velocities, and what do you call the acceleration of the particle and so on and so forth. We talked about it a little bit. So I'm gonna be more explicit now. Okay. So if say f equal to f of t, okay, represents the position of a particle. So imagine that this is time axis, and this is what we call the position axis. Okay, and I'm saying that okay, the particle is going what do you call up and down, and this is what is happening. Say imagine this time is in seconds. Okay, this time is in seconds, and this distance or the displacement is in meters actually. Okay, so particle is covering the distance in meters, for example. Particle or object. The particle pretty move fast. Okay, they move at but let's assume that that particle is really a person walking through a road actually, or maybe in a park. Okay. So this is the time in the seconds, or maybe a vehicle actually, maybe a bicycle. Okay. So this is time in the seconds, and this is the what do you call the displacement or the position, okay, of say a bicycle, okay, in what do you call that is moving in a what do you call in a park actually. So keeping in view this information, keeping in view this function, what you can conclude at? You can conclude many things, that in this interval it has covered a less distance, so the cycle must be low. It must be moving slow actually, in this period, and then it has a sharp up actually. So in this small amount of time, okay, it has covered a lot of distance. So that means that the object is gaining the velocity, so it's accelerating actually. Okay, and how about here? Okay, so you're going to say it slows down, but not slows down, but okay, so it's gaining more and more and more distance. So I can also make a plot for what you call velocity, and I can also make a plot for what you call acceleration. Now, how do you define a velocity? So we have talked about all this actually. How do you define velocity if you have been given the position of a particle? So if s equal to f of t is the position of the particle, or position of the cycle, or object, or person that is moving, or a car that is moving, okay? So position of particle. Now the particle is really an abstract object, okay? At time t, then how do you define, or what is the definition of the velocity of the particle actually, the instantaneous velocity? So for example, what would be the average velocity? So if you are talking about say a particular time period A to B, the average velocity is going to be that okay, so it's going to be B minus A over S of B minus S of A. Okay. So this is like at instant A, the particle has covered S of A meters or kilometers or whatever the units are. And at time B, it has covered S of B, for example, meters, and say this change, and the time is being measured in seconds. So what does this average velocity is going to tell you? This is telling you that how much of the distance is changing per unit second actually, say in meters. So this would be what you call meters per second. Okay. So it would be meters per second actually. That how much. The average velocity is giving you that on average in this given interval of the time, how much the object has moved on average. So just taking the ratio. But as I said that we are kind of more interested in the instantaneous speed. I mean, when you, for example, driving your motorbike or when you are driving your car, so your speedometer shows what you call a speed actually. That you are moving at the moment at this speed. So you are moving at say 50 kilometers or 60 kilometers per hour. So that 50 kilometer and 60 kilometer per hour is the instantaneous velocity of yours, or the instantaneous speed of yours at that time actually. Okay. So the instantaneous velocity of this is going to be what? That when you compute this change, average rate of change instantaneously, in other words, compute the derivative of the s with respect to t. In other words, that how s is changing in a small interval of the time. So their ratio would give you what you call velocity, and that's how you define velocity. And how do you define acceleration? So the acceleration is that how your velocity is changing over the time period actually. Are you gaining the velocity? Are you losing the velocity? Are you slowing down? If the particle is slowing down, or if the particle is gaining the velocity, okay? If t is going to be, what do you call, dv of t by dt. Now you can already see basically that this abstract notion of the derivative, when applied in physics, can represent, say, velocity, can also represent the acceleration actually. The same thing, the same derivative can represent the two independent quantities, two interesting quantities actually. And now there can be different, what do you call, interpretations for it. For example, if you computed this derivative and it turns out to be positive, so in other words, if the instantaneous velocity is, what do you call, positive, then what does it mean? So what is it going to tell you? So this is going to tell you that you are, you are moving in what do you call, the positive direction, and you are covering more and more distance actually. Okay, you're covering more and more distance. In other words, the s is increasing. Okay, the distance that you are covering, because this is ds by dt, and the derivative tell you that your thing is increasing or decreasing. So if the ds by dt is positive, then this tells you that your distance is increasing, and hence you are covering more and more distance actually. And how about if this is negative? So what does this mean is that the rate of change in the distance is decreasing actually. And what do you mean by the change in the distance over the time is decreasing? So this means that the particle or the object that you are tracking is slowing down. Okay, is slowing down. Okay, is slowing down. So this piece of information can be slowed down. Think about it. Think of yourself as that. Okay. So you are looking at, for example, an aircraft, okay, that is moving, for example, so the aircraft is like a particle, and you are looking at the aircraft on the radar actually, on the screen of the radar. Then the aircraft would be like a dot that makes a curve, and the different movements of that curve, different movements of that dot will tell you or give you the information about what you call that aircraft. Okay, and if so the s by dt is positive, then you're going to say that your aircraft is moving, is covering more and more distance actually. So it's like either it could either it's moving away or coming down, but it's covering more and more distance. And if it is negative, it's covering less and less distance actually. So it's like your aircraft, okay, is slowing down actually. Okay, it's slowing down. It's losing the velocity. Not losing the velocity, but it's losing the rate at which it was covering the distance actually. Okay, so it gives you a piece of information actually. And similarly, you can have the interpretation that, okay, if the acceleration of the particle, okay, or the object that you are tracking on your radar, okay, is positive, that means that object is gaining more and more velocity. And if if the derivative of the velocity with respect to time